I'm Jan Visser, the principal editor of a book on seeking understanding. I'm meeting here with Jan Hoang, who is the author of a chapter on popularization of science and mathematics. You are a mathematician, in addition to being a popularizer. What does it mean to you to be a mathematician?
I think one characteristic of most, probably all mathematicians, is mostly that we love mathematics and that we love beautiful arguments in particular. And really for me, like that's like the essence of being a mathematician is just to really love these beautiful, rigorous, like univocal arguments. This is really inspiring because then you can sort of try to apply these kinds of reasonings to other problems and try to think more carefully about other things. But yeah, the appreciation of the beauty of these arguments, I think, is really key.
So what you love is not so much mathematics as such, but what lies behind it.
Yeah, I think
correct.
There are like beautiful mathematical results as well that we really enjoy.
Yeah.
And definitely it's like part of it. But I think the appreciation of the arguments is probably even more, like especially the proofs or the key steps of a proof, is something that I think is very particular to mathematicians.
Mm-hmm. How does that work out in the major work that you do now in popularizing mathematics and science?
Yes, that's one of the hard things that I try to convey, is the idea that well, there's beauty in these kinds of arguments, and if you can appreciate this, it can really get you excited about mathematics more generally. But of course, there are plenty of other ways to discuss mathematics and to make it enjoyable. Like, for instance, one of the ways that I try to put forward as well, and I really appreciate, is just to have these not very clear arguments that leads to paradoxes. I think this can really trigger interests in these in mathematics.
Mm-hmm. There are some keywords that I find in your chapter that I think is very characteristic of this chapter, that people would not normally associate with their perception of mathematicians. It's in the first place love and passion and excitement and feeling and beauty. Yeah. Particularly feeling seems to be contrary to the spirit of mathematics to many people. Can you explain why they are wrong?
Yeah. So some mathematicians do not talk with a lot of passion, let's say, to the general audience, and there may be reasons, because mathematics is hard to explain. But when they're actually doing their real mathematics, I'm sure they're really, really excited about their stuff. And so they don't show it, because it's hard to show, because the things that they are interested in, well, it's hard to share because it's complicated. But I think when I talk to mathematicians, the thing that really comes out is really how exciting some results are. And I think it's really, really important to put forward this idea, because I feel like there's a big divide between like people who love mathematics and people who hate mathematics. Like some people don't have strong feelings about mathematics, but a lot of people have math anxiety. Like, it's often there's even a Wikipedia page.
Where does that come from, actually?
So there are probably many reasons, but I think one of the reasons is the fact that the school systems is, especially the selection in school systems, is strongly based on the notes that people get in mathematics courses. So mathematics is often regarded as perhaps the field of selection, like the one field you should succeed in to show that you're a good student or that you have skills. And thus, this leads to
and it would affect your future.
As well, yeah. And also, I think in terms of there's a social pressure to be sort of like good in mathematics. That people who are good at mathematics are regarded as like this kind of intellectuals that are like have a special like you have a social bonus in some sense to be to sort of show your skills, and thus when you given a mathematics problem, it always feels a bit like a test. And even I sometimes when I'm given a mathematics test, if it's a public test that it's on live on some YouTube video, for instance, I will be extremely stressed because like publicly I don't want to fail in a math problem. Like it's I feel judged when I'm doing mathematics publicly, and I shouldn't. I should regard it as a fun game. And that's me, like already having a PhD in mathematics. So, like I think most people really consider that math questions are really tests, and that they're going to be judged in some way. And of course, you're going to have anxiety if you approach mathematics this way.
So when they present you the bill in a restaurant, and you have to add up the numbers, it makes you feel.
Well, I usually answer, "Oh, come on, I cannot do this. I'm only a mathematician."
Yeah. You pull out your calculator.
Yeah, I do this with a calculator. Yeah.
Yeah, but it's definitely has something to do with the way mathematics is being treated within the school system, right? Yeah. So the mathematics teachers, well, they're of course very good ones, but the garden variety of them may not have that same perception of mathematics that you try to convey through the chapter.
Yeah. I think being a teacher is very difficult in mathematics.
And the curriculum.
You have a curriculum to follow, and you sort of often now you have these standardized exams, and you really want your students to succeed in this exam, and this also gives you pressure, puts pressure on the teacher, who then puts pressure on the students to succeed in these exams. And so you have all this pressure that sometimes are explicit, but even when they are implicit, or when you don't even know that you have this kind of pressure, it acts on your appreciation of mathematics. And then if you start to be anxious about mathematics or scared by mathematics, it's extremely hard to do mathematics afterwards, because mathematics requires exploration. And like mathematicians are always exploring. We have these drafts and these piles of nonsense, like in my office at least, and all of these usually go in the garbage. And I don't want anyone to be looking at this because there are a lot of things that are extremely wrong. But it's part of the process of learning mathematics. You have to do a lot of mistakes. And if you're scared to do mistakes, you're not going to do these mistakes, even in private. And if you don't do this, you do not explore, and it's impossible then to advance in mathematics.
Yeah. And the pressure in general that exists in the school system is not very beneficial to appreciating beauty in general, not only in mathematics, but I think it applies to many other disciplines like language arts, poetry, the way that students deal with poetry that wouldn't often not lead to them really appreciating what lies behind the words in which a poem is expressed. And same in mathematics, it's a kind of poetry itself, isn't it?
Yeah, definitely. There are lots of fields that when I was in school I got, let's say, bored by, and I only came to appreciate it later on, much later sometimes. And that's, I felt sometimes lucky because it's often related to people I met or like places I visited. But in terms of mathematics, it's harder to get hooked again if you to get back into this appreciation of mathematics. And that's because, like, and part of another reason why that is the case, and another reason why I think there's a lot of math anxiety, is the fact that like it's not common to be doing mathematics outside of academia, and so it's often like people often associate mathematics with kids. Basically, we tend to think that mathematics is either something that kids do or that mathematicians do. And if you're not a mathematician and not a kid, then there's this idea that, well, you don't need to do mathematics. There's also this idea that mathematics is not useful, and if it's not beautiful, then why would you do this? Mm-hmm. And I think typically if parents are in this mindset, it's hard to get the kids excited into mathematics. Well, it's not only specific to mathematics, science in general, but I know that I have friends who do this kind of science popularization work, or they invite like parents and their kids to an event or to an explanation of something, and the parents arrive, let the kids watch and do something and go do something elsewhere, and it really gives the impression that the science is only for the kids, and the parents, they can do something else. Mm-hmm. And that's very bad for the appreciation of mathematics by the kids in particular.
So you prefer to focus on the grown-ups?
Yeah.
Rather than the kids?
Yeah, so there are multiple reasons why I prefer to focus on the grown-ups. Like one of them is what I've just said, that is the grown-ups influence the kids indirectly. Another reason is that the grown-ups, well, most people are grown-ups, or at least above 20. So if you only do for people between 0 and 20 years old, well, you're missing out on most people. Still another reason is that these people are the ones who are voting and taking decisions, and so it's important to influence them. And perhaps the most important reason is that not much is done for the grown-ups. If you think about the investments made in mathematics education or teaching, it's like a huge amount of money for only these people, and very little money for the rest of the population. Mm-hmm. And so if you think about where do I want to invest my time to have the most effect, one person who adds to, if you invest $1 more, or if you start your career working for the younger people, you're adding to a pool that's already big, like becoming from 1 billion to 1 billion won in terms of dollars, or like from 100,000 teachers to 100,001. So you don't change a lot of the situation. But if you invest your time or your money in the rest of the population, given that there are not so many people, then maybe you move from 100 to 101, and so you have a bigger contribution.
There will probably also be a great benefit to family life if grown-ups are familiar with the matter that their kids are supposed to become familiar with. It incentivizes interaction within the families, and whereas now, as you're explaining, doing math is perceived as, well, that's the stuff that kids need to do in school, and after you've done it, when you become a grown-up, you are done doing mathematics. Which is of course not what you want. There's something interesting in your chapter. Well, there are lots of things that are interesting in your chapter, but one of those things that I selected is your emphasis on having problems in mind. Rather than sweating about them, sitting at your desk, but quietly letting them be there and allowing you to ponder about them in all kinds of circumstances. And depending on the case, one sees the light sometime, and you're patient to do that. Can you give some examples in your own life of how that?
Well, I have so many examples in my own life. So I give one example in the chapter, but like another example that really it's something over the last 2 or 3 years I've been thinking a lot about one equation in particular called the Bayes rule, which is an equation in the probability theory. And this one equation, like I've been thinking almost like every 2 days, I guess, or maybe like at some point, like every day, if not several times a day. But these days, maybe more. It's more like once every 2 days. But this equation is always sort of following me, and every now and then I get to think about this equation. More often than not, it's unconsciously. It's like or like because of something I'm witnessing. I'm like, hey, this reminds me of something, and like slowly after 5 or 10 minutes, I get to think about the Bayes rule because it's somewhat connected. And I've learned so much about this one equation over like the last 3 years. And just like yesterday, I discovered something else that was implied by this equation, or why this equation is the way it is. And it's really fascinating. There's a huge excitement for one thing. Whenever I get my mind to think about this equation and discover something like that, and it really happens. It's small discoveries, but it's still very exciting.
It's always unexpected.
It's very often unexpected. Yeah, it's start to think about something, and that's unrelated to this equation, or maybe sometimes it's like I consciously think about this equation. I'm like, hey, I have a bit of time. Let me think about Bayes rule, but I don't know where I'm going to discover about this. And sometimes it's like I try to think about this equation in one way, and it informs me about a whole other way to look at this equation. Mm. So it's very unpredictable, for sure. Right. Yeah. And I think this kind of background reasoning that mathematicians often have, there's a lot of stories of mathematicians having these kind of things, and like a lot of mathematicians and physicists and a lot of scientists have talked about this. So it seems like it's very common for scientists, and I think this is a very important part of the learning. Mm-hmm. Like you cannot have a good learning if you don't have these thinking times outside the
so
office.
You must give yourself the time, and in the school system kids should be given the time to go through that experience. It's like finding your keys. When you start agonizing about it, you never find them. Yeah. As soon as you stop agonizing about it, you all of a sudden say, oh no, I know where I put them.
Yeah. So I've been thinking about why this could be, but there could be also like algorithmic explanations of why the brain sort of works this way, and they're all related to Bayes rule, so it sort of closes the loop. But basically, in algorithmics, you have this idea of Markov chain, Monte Carlo Markov chain, where you're sort of exploring a space of ideas with random steps or something like that. And if for a long time it can give nothing interesting, but you just need to keep exploring, and sometimes it will hit on some point, on some idea that is much better than all the rest you've explored so far. But it takes time to get there, and so you sort of need this process of keep thinking about it to do this exploration.
Yeah, that sounds like related to your Bayesianism as foundation of all knowledge, right?
Yeah. So it's also related to a lot of work in neuroscience, like recent work about how the brain is thinking and how to model the way the brain is thinking. And there's this so-called Bayesian brain hypothesis, which is not really clear what it is exactly, but basically says that a lot of the thinking that goes on in our brains is very similar in some sense to Bayes rule.
Mm-hmm. Interesting. You wrote an entire book about it.
Yeah. It's a topic I really love.
It's the English speakers who are watching this video they may not know the language in which it is written, French.
Yeah, so far the book is it's called La Formule du Savoir. It's in French only, but translation is.
It's going to be translated?
It is being translated
right
now, and hopefully it will come out soon in English.
So the audience should keep an eye on when it comes out in English if they do not master the French language. And actually we are recording this here in France.
Yeah.
What you're mentioning here also reminds me now of the title, the main title of the book, that the chapter is part of, Seeking Understanding. And if you take the two words, apparently the fun, the great excitement one feels has to do with the seeking, not with the understanding as such. I mean, you're glad when you understand something, but as soon as you understand it, you're also aware that there's lots of things that you do not understand, and that's actually a great benefit because it allows you to go on seeking understanding, and the seeking of understanding that's what humans are best at, probably.
Yeah, definitely. And in fact, in some sense, a problem can be much more enjoyable. Well, is usually even much more enjoyable than the solution of the problem. Try to always have a few problems to keep in mind, just understanding better base rule or problems related to different things. And it's really nice to have these things just to think about, because it's easier to start with a problem than start with the solution of the problem.
So they kind of took the fun away with the last theorem of Fermat.
Cannot solve it now.
Another issue that I'd like you to say something about, you write about it extensively in the chapter, the experience that you had, because most of your work is via the web, YouTube particularly nowadays, but you also had the opportunity to interact directly with high school students in a splash math session at MIT in Cambridge, Massachusetts. And from what you described there, you're dealing with pretty heavy stuff. Einstein's general relativity theory, and not aiming necessarily at profound understanding by the students of what it's about, but giving them the feel of things. Can you explain how that works?
Yeah, I think there are a lot of things that can be said about these very complicated theories that can trigger a lot of fascination and questions, things that people can then ponder when they go home. And what I'm trying to do a lot in the popularization work that I do is to get people frustrated by the fact that they don't know the full story, and they feel like they can know more, and they perhaps even easily could know more if they just thought longer or just read the solution elsewhere. But that's really a feeling I'm trying to get people to feel. And like, frustration is really fascinating. It can lead to a lot of new ideas. And so what I'm talked about general relativity at Splash. I also talked about other things in other lectures. The idea was never to get them to have a full understanding of general relativity, because as some people know, it takes years to learn general relativity. But you can easily get some ideas through. Like basically when Einstein was thinking about these issues, it was trying to work out a few problems, and one of the problems that Einstein had to face is, like, for instance, how to come up with a system where with laws of physics where nothing would break the speed of light, and so you couldn't have this instantaneous effect of gravity. And another one that Einstein really thought a lot about is, what if gravity is not a force? Like, what if it's not something that pulls objects down? And it's a fascinating thought, because if you go back to history before Newton, essentially, like you didn't have this idea of force either. So back then they were thinking of gravity in another way, and the gravity that pulls the apple was not the gravity that pulls the moon before that. And then we changed, and then physics really got into these Newtonian ideas, and it really became the paradigm of physics. And it led a lot of students to build some kinds of intuitions about physics. But what's marvelous about Einstein's work is that it's sort of incompatible with a lot of these intuitions that we have. And I like the idea that there's this tension between these different intuitions, and that there's something to be solved, there's a problem, and we can think about this problem.
It makes you think differently about common things.
Yeah, exactly.
Create a different picture. Interesting. You also write about not just dealing with problems, but in your work trying to build up things so as to ensure that problems that one is preoccupied with can be situated in a larger context, right?
Yeah. Yeah, that's something that I got very frustrated by when I was doing research. Is the fact that in research we really specialized in one particular topic, which is a subset of a subfield of some larger domain, of one of the domains of science, which has many. And it's very hard to have any sort of global picture. Personally, when I started my PhD, I couldn't even draw a landscape of applied mathematics research. It was just too wide, and also I was really wrong about some of the parts of applied mathematics, especially artificial intelligence back then. Like many people regarded this as not promising, let's say, and I definitely regard it as not promising. So yeah, it's very hard to have a global view of all of this. And I think there's a lot of work to be done in trying to have a better, produce work that sort of tries to have a global view of it all and how everything fits in this sort of global picture. Maybe there's not even one global picture, or different ways to look at how things are done. And this is some kind of work that I really enjoy, and I feel there's a lack of.
It also means putting things not only scientifically in a broader context, but in the context of where science fits within society.
Yeah, exactly.
Right?
That's also a question I'm very interested in, is the fact that a lot of the science advancements, so it's especially the case in biotechnology these days, or global warming, or artificial intelligence. These things have a huge impact on societies, and it's I think it's important to have people thinking at least about how what are these effects, and how to best mitigate them. And it's not that often a reflex that scientists would have. It's often the case that when I discuss, for instance, artificial intelligence with artificial intelligence experts, they are just focused on the artificial intelligence research or
on the mechanism and the algorithms.
Yeah, and the algorithms. And I think there's really a need to be thinking more about the impacts of these algorithms, and especially how to make these impacts as beneficial as possible.
This brings me to the final part of our conversation. So let's talk a bit about the world in which we live, the world of the Anthropocene, the world that has become increasingly interconnected thanks to the development of technology, which can be beneficial but also has quite a number of risks in itself. The capacity of people to understand that world is well related to the quality of their mind. Yeah. And the work that you are doing, as I see it, may well be instrumental to improving the mindset of people in order to be able to intervene correctly in a way that avoids the imminent disaster if we don't change our behavior.
Yeah, there are definitely worries, a lot of concerns to be had about these issues, and like it's very complicated. I think it's very important to insist on the fact that trying to find solutions, for instance, to climate change or to reduce risks related to there are numerous like so-called existential risk or catastrophic risks that are being studied by many institutes like the Center for the Study of Existential Risks or the Future of Life Institute or the Future of Humanity Institute. And so there are lots of concerns, and it's never easy to know how to address these concerns. And it's hard, I would argue, at all levels, like even, well, clearly at the level of policymakers or the level of the electorate, it's extremely hard to get many of ideas through. But we also have to recognize the fact that even among experts, it's very hard to know what we should do to mitigate all these risks. And yeah, for sure, like trying to build better foundations for knowledge and promote clearer thinking is definitely very important to address these issues. Another thing that I have witnessed a lot, and there's also a lot of research in psychology about this, is that it's very hard to convince anyone of anything if he has an intuition that's not what we want to convince him of. Because we tend to think to have intuitions and then to defend our intuitions, and it's very hard to get out of this and try to think more carefully. So what I'm trying to do, also of course I'm trying to promote better thinking, but also one thing I'm trying to promote as well is the idea that we should motivate people into thinking better. It's not sufficient to teaching them or giving them rules to be followed to think better. You also have to show them that there's something to be gained by thinking better. And of course, one thing that could be gained is reducing such risks. But if they don't believe in the risks, it's not going to motivate them. So you have to adapt to them and try to find ways to still motivate them into thinking better that are not your own motivations. Necessary. And so one thing I think is important is to insist on the fact that it could be very nice just to think better. Like there's a real pleasure to thinking better. So that's one of the things I'm trying to push and to get people excited into better thinking.
So it's not just a matter of the intellectual capacity to understand or to seek understanding, but also of the will to do so.
Yeah, and it's
volition is probably the key word here.
Yeah, exactly, and it's very hard to get. I feel like there's not enough work that try to get to this sort of idea that the fact that you really have to find a way to motivate people into thinking better. It's not sufficient like just to tell them to think better or to teach them to think better. It has to come from within. And the teaching of mathematics, or at least the way I see how mathematics is taught, is really about this. It's not like we've been teaching mathematics rules, and I can give like the axioms and the right inference, the right rules of mathematics to anyone, but it's not sufficient to get him or her to do good mathematics. To do good mathematics, you also need this excitement about mathematics. You need this passion and love for mathematics. And similarly, I want to promote love and passion for better thinking, and not just give the rules for better thinking.
So we need to approach the problems of the Anthropocene also with love and passion.
Yeah, I think
and the desire to find beauty.
Yeah, I think it's. I actually think it's very key. Like you have to enjoy yourself doing good. So there's this movement called effective altruism, who tries to promote ideas for how to be effective in your altruism. And one of the key things is really getting people excited into these ideas, because and that's not easy. Like, and I would argue there's not sufficiently things that are done in this direction.
Lee, thank you very much.
Yeah.
Thank you very much for the conversation, but also for the chapter that you contributed. It's a beautiful chapter, and I recommend everyone to read it. Thank you very much.
Thank you very much.